99% of the visible matter in the known universe is in an extraordinary state. This state puzzled physicists for a long time. But scientists wanted to understand it. They were hoping they could access an almost inexhaustible source of energy. They wanted to bring the cosmic energy of the stars, the force of our sun, to Earth.
Our sun has been shining for 4.6 billion years. A glowing ball made of hydrogen and helium. The star's power plant is located in its interior. Here, temperatures of 15 million degrees prevail. The hydrogen atoms are composed of nuclei and electrons. This state of matter is called plasma. Hydrogen nuclei fuse with one another. Helium nuclei are produced, and a great deal of energy.
But 15 million degrees? But are the particles really fast enough? They have too little energy to be able to fuse in sufficient numbers.
That's right. But in the sun's core, enormous pressure prevails, ensuring that fusion reactions take place.
But exerting such a high pressure here on Earth will never work.
That's right too. And that's why scientists had to resort to a somewhat different reaction, and above all, produce much higher temperatures for fusion, over 100 million degrees. Heating the plasma was not the problem. The real difficulty was to maintain plasma temperature in the chamber. For if plasma comes into contact with the chamber wall, it immediately cools down again.
So, scientists just had to levitate hot plasma of 100 million degrees in a burn chamber without it touching the walls? No problem.
You're laughing, but this is precisely what scientists had to try. And they used a force that you all know. Magnetism.
Yes. Plasma consists of positively charged atomic nuclei and negatively charged electrons. Therefore, it can be influenced by electric and magnetic fields.
Just like this pen. And it can even be confined in magnetic field cages. And then in such a way that it does not touch the wall of a fusion chamber.
Can't I shape the plasma any way I want, just by generating the appropriate magnetic field?
Unfortunately not. The particles mustn't be allowed to escape at the poles of the magnetic field. Only ring-shaped plasmas can do this. Furthermore, the magnetic fields have to be specially shaped to insulate the heat of the plasma. To achieve this, one has to understand the plasma very well. Work for more than 50 years.
Since the end of the 1940s, scientists in many countries had been trying to clarify the properties of plasma. However, good experimental results were rare. It was not till the end of the 60s that Russian scientists announced astonishing successes with their so-called Tokamak device. Worldwide Tokamak fever erupted. But after 10 years, the best results were still a factor of 25,000 below the requirements of a fusion power plant. But then the large joint European experiment, JET, went into operation in the United Kingdom. In 1997, the scientists there obtained results just a factor of 6 short of the ignition conditions of a plasma. The sun's fire came within reach for the first time.
At the beginning of the 21st century, it was still not clear if a fusion power plant was possible.
But continual increase of oil and gas prices brought the threat of economic crisis and war. And it was also clear that our climate didn't need even more greenhouse gases. The time for new sources of energy was more than ripe.
Exactly. For fusion, everything now depended on one project that was mainly made possible by European research, the international experiment ITER.
In 2007, in Cadarache in southern France, construction of the largest experiment in the history of fusion research began. Besides Europe, Russia, Japan, and the USA, the project also included China, India, and South Korea. The test reactor aimed at demonstrating that it is physically and technically possible to gain energy from fusion. In ITER, the essential fusion power plant technologies were deployed for the first time. 800 cubic meters of burning plasma was to generate 500 megawatts of power, about 10 times as much as was needed to heat the plasma.
But what I don't understand is how the energy in a power plant is extracted from the burning plasma. How do you actually extract electricity from the fusion energy released?
The raw materials for fusion are available on Earth in almost inexhaustible quantities. And in 1 gram of fuel, there's the combustion energy of 11 tons of coal. The fusing of the 2 hydrogen isotopes, deuterium and tritium, creates a helium nucleus and a neutron. 80% of the fusion energy is in the neutrons. They are not charged and therefore fly out of the magnetic field cage. They are slowed down in the walls of the plasma vessel. Thermal energy is produced and it can be converted to electric energy, just as in the old coal-fueled power plants.
The energy of 11,000 kilograms of coal in 1 gram of fusion fuel. That sounds really tremendous.
But the plasma is very thin. 1 gram of fuel is diffused in over 1,000 cubic meters of burn chamber volume. Furthermore, the plasma can only be maintained under very specific conditions. Any perturbance, however small, terminates the fusion reaction. A runaway effect is thus not possible. Okay, time for a little test. You have exactly 30 minutes to research the end of the story. I want a complete dossier. What did we learn from ITER? When did we get the first fusion power plants? And how much fusion energy are we annually consuming today in Europe? In the next physics lesson, we will discuss about the possibilities of beaming.